Hello, welcome to NPTEL online certification course on Introduction to Application of AI to Robotics. Today we are going to see the Lagrangian formulation of manipulator dynamics. Okay. In the last lecture, we have seen an example of Newton-Euler formulation, where we have seen that in a recursive way we evaluate the first during outward iteration, we evaluate the accelerations and then inertial forces and moments, and then during inward iteration we evaluate the torque, joint torque. Okay. So, in this formulation, let us see how we are going to get the dynamic equation of a manipulator. Okay. So, I expect that after going through this lecture, you will have a thorough understanding of how we can derive the manipulator dynamic equation using the energy based approach. Okay. So, here initially I will introduce the topic to you, and then we will be seeing some basics, and then I will be deriving the dynamic equation of a manipulator, and then we will be seeing the two examples, one of that of a single DOF robot and another one of that of a 2-DOF robot. Okay. So, Newtonian mechanics requires free body diagrams for every link, and this becomes complex if you have a multi-degree of freedom robot. Okay. So, Lagrangian mechanics on the other hand uses scalar energy functions, okay, which is much simpler to derive. Okay. And it automatically handles constraint forces, and equations are expressed in generalized coordinate, okay, which could be either the joint angle if it is a revolute joint, or it could be joint displacement if it is a prismatic joint, and it scales elegantly from 1 degree of freedom to n degree of freedom manipulator, and it is a foundation for model based control and AI driven dynamic learning. So, as I said, Newton-Euler method, what we did essentially, we had the force and torque balance for the each link, as we have seen already, and our computation is recursive in nature, which is very good for the real time task. The Lagrangian on the other hand is a energy balance over the system, and a systematic derivation, and this is good for the model formulation. Both yield the same equation of motion, that is quite obvious. Okay. So, the Lagrangian is preferred for analytical insight and the AI integration. So, this AI integration part that I will be taking up once we cover the AI portion of this course, then we will be seeing the integration part. So, there again I will be coming up to this AI integration thing. Okay. So, let us have refresh some of our basics. Okay. So, the first is the kinetic energy. It is a form of energy that a body possesses due to its motion. Okay. We have studied in our school about this. Okay. Now, this kinetic energy of an object is equal to what? The work needed to accelerate the object, okay, from rest to the given speed. Alright, or it could be equally the same thing, that is, if the work done by the object when decelerating from the current speed to the state of rest. Either way we can have it. Okay. So, suppose if we have a translatory motion, okay, and a mass of the body m, say it has got a velocity, okay, then the kinetic energy or the translational kinetic energy of that is going to be half mv square. This is the basic formula which we have studied in our earlier classes. Okay. Now, if the object has got a rotational motion, right, and naturally rotational motion has to be about a certain axis. Okay. So, if the object has got a rotational motion, okay, and say the object has moment of inertia I, and say the angular velocity here, the rigid body is say omega, then the rotational kinetic energy is given by half I omega square. Okay. Next is the potential energy. The potential energy of a body is basically its capacity to do work in virtue of its position. Okay. And how does it is measured? So, it can be measured by the amount of work done by the forces to restore the body from its present position to its standard position or some reference position. So, that is how we evaluate that. Okay. So, if the force is say Fr, okay, and current position is R of the body, and we want to take it to the its reference position R0, then this is going to be the work. So, we have elemental displacement, and then we take a dot product, and then we integrate that. Okay. So, that way we can do that. So, if the present position of the body is specified by a vector r, and say I am taking that body to the standard position or the reference position, okay, and that I am defining by vector r0, the work done will be basically FRdr, and that integrated over say R to R0, and that is going to give me the potential energy. Okay. And once we have the potential energy and we have the kinetic energy, we can derive the total energy, and this is the summation of the kinetic and potential energy. Okay. So, the Lagrangian is defined by as a difference between the kinetic and potential energy. Okay. So, in this expression basically this Qn, L is called Lagrangian, Qn is actually the generalized coordinate. Okay. Generalized coordinate basically means a general coordinate. So, it could be say linear position, or it could be angular position, like that. Okay. So, both linear and angular we are putting it together and giving it a general term which we call it as a generalized coordinate, and say Qn dot is the derivative of the generalized coordinate. Okay. So, K, as I said, it is kinetic energy of the whole system, and capital U is the potential energy of the whole system. Okay. So, if I take the difference between kinetic and potential energy, I get the Lagrangian. Okay. And so, the equation of motion based on the Lagrangian approach is given by this expression. Okay. That is d by dt of del L, that is partial derivative of Lagrangian with respect to generalized velocity, okay, minus del L upon del Qn, and that equal to Fn. Okay. So, here Fn is the generalized force or torque. Okay. So, that is there. This equation has limitations such as when the dissipative forces are present, we need to introduce some additional term which we call as the Rayleigh's potential function, and we cannot handle the gyroscopic forces or moment, and we cannot handle the non-potential forces such as circulatory forces. Okay. So, these are the some of the limitation of this Lagrangian formulation. We need to do certain changes in this equation in order to take care of the dissipative forces, that I am not going to discuss currently. Okay. So, when I have to write the expression, the dynamic equation of a manipulator, and you know a manipulator is made up of a number of links, right? So, a manipulator may have the number of links. Okay. So, first I can get the kinetic energy of say ith link of the manipulator. Okay. So, this kinetic energy of the ith link of manipulator is going to be a half mi, that is the mass of the ith link, into this is the center of mass velocity, okay, of the ith link square. So, that is why we are multiplying here the center of mass velocity vector transpose with that velocity vector. Okay. So, this is nothing but the kinetic energy due to linear velocity of the link's center of mass. Okay. And the link has also rotary motion, right. So, it is going to have the angular velocity as well. So, it will possess the kinetic energy due to the angular velocity as well. Okay, and so that will be half I omega square basically for a single particle, which we know, but for here the rigid body we can write it. This is basically omega I, and this is the inertia tensor written about, expressed in terms of the center of mass frame, and that multiplied with the ith length angular velocity. Okay. So, this is the kinetic energy due to the angular velocity of link. Now, so for one link we have the kinetic energy, that is the translatory kinetic energy and the kinetic energy due to rotation. Then we can find out the total kinetic energy of the manipulator, which is going to be sum of the kinetic energy of the individual links. So, I can take the summation here from I is equal to 1 to n if my manipulator has got n number of links. Next, coming to the potential energy of the ith link. So, that I can give as, we know this standard term, right, mgh, alright. So, here basically it is a mass of the link, and this is the 3 cross 1 gravity vector, okay, expressed in terms of say 0th frame. Alright, I am taking transpose because I have to do the multiplication with this one, that is the center of mass position vector, which is again expressed in terms of the 0th frame, plus we are adding some reference value, so that this total is not going to come as a negative, okay, so that the minimum value of ui is 0. So, once I have got potential energy for the ith link, I can find out the potential energy of the whole manipulator, okay, by simply summing up the potential energy of links from link number 1 to the link number n, right. Here we see that this, the position vector Ci of the ith link, which is expressed in terms of the 0th frame, is function of theta. Okay. So, the potential energy of the manipulator can be described by a function of the joint position, alright. So, this way we can do. So, the Lagrangian of a manipulator, if we want to write it, I have evaluated this term for all the links, okay. Similarly, I have evaluated this term for all the links. So, I can evaluate the Lagrangian. Okay. So, we have seen that this u is going to be function of theta only, right, whereas the kinetic energy is going to be function of theta as well as the theta derivative. Okay. So, this is our Lagrangian is going to be function of theta and theta derivative. Okay. So, now I can write the equation of motion for the manipulator, this one, okay, that is d by dt of del L by del theta dot minus del L by del theta, and this is equal to tau. Okay. So, this tau is n cross 1 vector of the actuator torques. Of course, if it is a all the joints are revolute joint, and if any one of your joint is the prismatic one, then corresponding to that joint we are going to have the force, alright. So, this is there, and now what I can do that, I know my Lagrange is a function of k minus u. So, here I can substitute this Lagrange expression. So, this is what I get. So, del k upon del theta dot minus del k upon del theta, because this is k is function of both theta and theta dot, and minus actually u theta, but you see that u is function of only theta. So, when I am taking partial derivative with respect to theta dot, so I am not going to get any value for this, that value will be 0. And then when I am substituting here minus del L by del theta, so I will have minus del k by del theta, and this minus and this minus, this minus and this minus, they are going to make it as a plus. So, I am going to have del u by del theta, and this is going to be equal to torque. Okay. So, this I talked about a generalized coordinate. Okay. So, if my joints are all revolute joint, then these generalized coordinates are going to be nothing but thus the joint angles, okay, expressed in terms radians. Okay. And if it is a prismatic joint, then naturally this my generalized coordinate is going to be all the joint displacement in meters. Alright. And depending on what type of manipulator you have, or which you want to derive that expression, this if it may have suppose both the revolute as well as prismatic joint, then in that case we may have both theta and d terms, both are going to be there. Okay. So, there are some key properties of generalized coordinates. These minimum set of coordinates needed to describe the configuration, that is there is no redundancy. Then problem a dimension for a 6 degree of freedom robot, naturally you are going to have the 6 generalized coordinates, and velocity actually gives the generalized velocity used in kinetic energy formulation. So, you can take the derivative of the generalized coordinate in order to get the generalized velocity. Okay. So, now let us use the Lagrangian equation which we have derived over here in finding out the equation of motion, say single degree of freedom and 2 degree of freedom manipulator. Okay. So, to keep the problem simple, suppose this is very single degree of freedom manipulator, it could be just like our this hand, right, mechanical hand with certain mass at the say grip here. Okay. So, it is a just mechanical hand. So, you have this mass and you have say here one torsional spring of stiffness kT is there, and this is say my xyz reference system. So, say this angle at any instant is theta and say this length is L, alright, and this is the direction for J. Okay. So, it is a very simple example, but I just want to give you a feel of how we are deriving the equation of motion, right. So, the kinetic energy, so let us in order to find out the Lagrangian, as you know L is basically k minus u here. So, first let us find out the total kinetic energy here. So, the kinetic energy is going to be half ml square theta dot square, basically it is a I omega square, right. So, this is the kinetic energy, and if we assume say this y is equal to 0, if this is my datum, the potential energy will be given as half kT theta square. This is the potential energy stored in the spring, and minus this will be actually this distance is going to be your L sin theta. Okay. So, it will be mgh basically, and that h is going to be L sin theta. So, this is there, right. Now, I can find out Lagrangian by subtracting kinetic energy and potential energy, and then I can substitute it here, or what I can do is that I can write this Lagrange equation in terms of the kinetic and potential energy, and then I can substitute the kinetic and potential energy directly. So, this Lagrange is a difference between kinetic and potential energy. So, this is the way I can write a Lagrange equation, and here my generalized coordinate is theta only. Okay. You know it is a revolute joint here. So, my generalized coordinate is theta, that is 1 degree of freedom system is there. So, I have got only one generalized coordinate. Okay. So, now since now to evaluate all the terms over here, first I have to take partial derivative of k with respect to theta dot here. So, my del k by del theta dot is going to be ml square theta dot, and then I can evaluate this term, right. So, it is this term. So, I have to take derivative of this one. So, this is ml square theta double dot, and then for this term this is going to be 0, because here in case kinetic energy I do not have any theta term coming over here. So, this is going to be 0, and then I have got u, right. So, this was my u. So, I can now evaluate this term. So, del u by del theta. So, this is going to be kT theta minus mgl cos theta, right. So, now I can substitute, this is the one term, okay. This is another term, and this is my the third term. Okay. So, if I substitute all these three terms in my Lagrange equation, this is what I am going to get, ml square theta double dot plus kT theta minus mgl cos theta is equal to 0. And this equation is the equation of motion of this single degree of freedom manipulator. I can replace this spring by a motor also. Okay, so in that case you are going to have in place of kt theta you are going to have the motor torque, okay, which is going to come. So that way if you want to do you can make that and you can practice that. Okay. And if you remember, this problem is almost similar to that of a pendulum. Okay. In pendulum we usually assume that here there is a hinge, okay, but in this case I have taken a torsional spring so that we can actuate this joint. Okay. So I can take this problem similar to that of a pendulum as well. Okay. So in this case you see this is going to be the weight of this bob basically, okay, mg, and okay, so this angle is theta, so this angle is going to be my 90 minus theta, so this angle is going to be 90 minus theta, okay, so this angle is theta basically, okay. So what are my unbalanced torque which are going to act over here? Okay, so it will be what? How much torque is going to be acting on this one? So because of weight, this component is going to be what? That will be mg this component, so mg cos theta. Okay, so this is mg cos theta, or I can say that mg sin 90 minus theta, it is same thing. Okay, so I can, let me write it directly. So mg cos theta and that multiplied by L. So this is going to be the torque, and spring will be putting the resistive action into that. So I can subtract from this one the kt into theta. Okay, so this is going to be the resistive torque. Okay, and so this restoring torque will be basically going to be responsible for angular acceleration of this bob. So this is unbalanced torque basically, so that I can equate with I theta double dot. Okay, so ml square theta double dot. So this is the same equation which we got it over here. All right. So this is the way we can do this one. All right. So here we did using Newton's second law, and here basically we did it using the Lagrangian formulation. Okay, next let us take a simple 2 degree of freedom manipulator. The previous one which we have seen, we had only one generalized coordinate theta. Now suppose this is a 2 degree of freedom manipulator. Here this is one link basically, okay, which has got rotary joint here. So its position can be described by this coordinate theta, and there is a prismatic joint here, say this one. Okay. So the CG of this link is described by the generalized coordinate d2. All right, and this one is generalized coordinate theta 1, and say this CG location is L1 here, and so naturally this is the CG location, and say this mass is m2, the seconding mass. Okay, and we are given the inertia tensor for the two links. Okay, and so since this is a planar one, okay, the planar manipulator. All right, so my rotation are going to be, this is my z axis, okay, say z0. So all my rotations are going to be about z axis only. So essentially I will be interested in these two terms from this inertia tensor. Hope it is clear. Okay. So kinetic energy of the link 1 we can evaluate, okay, and what it will be? It will be half m and L1 square theta 1 double dot, okay, and so this will be basically half mass into the velocity of the CG of this link, okay, and you see this velocity is r omega. All right. So basically here this will be L1 square and your theta 1 dot square. Okay. So this is the translatory kinetic energy plus this is the rotary kinetic energy of the first link. All right. Similarly, I can get the kinetic energy of the link 2. Now, for the kinetic energy of the link 2, mass is having the two velocities. The CG of the mass is having two translatory velocities. One is in this direction, and in this direction it is there because of this rotation, okay, because this will be rotating along with the first link, and since this joint is a prismatic joint, it is going to have the velocity also in this direction. Okay. So we have to find out the velocity square. Okay, so that is going to be this d2 square theta 1 dot square, which is this velocity, and d2 dash square, this is this velocity in this direction. Okay. So, this is your d2 dot, that is velocity in this direction, and in this direction this is d2 and theta 1 dot. Okay. So, these two are the translatory velocities. So, we can find out the resultant of that. So, this is the total kinetic energy because of the translation for the link 2, and this is the I omega term basically. So, the second link is having angular velocity the same as that of the first link. So, this is theta 1 dot square, and this inertia tensor component in the z direction is IZZ2. So, I keep it there. So, the total kinetic energy is now I can just add up this equation and this equation, I get the total kinetic energy. So, here I have written as a coefficient of theta 1 dot square, and the other term is basically d2 dot square. So, this I have done. Okay. Next, the potential energy of the link 1 will be basically what? It will be this distance basically, which will be L1 sin theta. Okay. So, M1 L1 G sin theta 1 here we are going to have, because this angle is going to be theta 1 here, plus a constant value, right, which is M1 L1 G. So, that way we can have that. So, the potential energy of the link 2 likewise I can get as say M2 d2 G sin theta 1. So, it is basically this distance. Okay. So, this is going to be d2 sin theta 1, this is my angle theta 1 plus a constant value. Okay. So, the total potential energy can be given as, I can combine these two terms, that is the u1 and u2. Okay. So, this way I can do that. We have already evaluated u1 in the previous slide here. Okay. Now, I take the partial derivative, okay, in order to write the Lagrange equation. Okay. So, this was my kinetic energy expression which we have evaluated. So, del k by del theta dot. Okay. So, it is basically what it is going to be. It will be, we have to take del k by del theta 1 basically, and then del k by del d2, del theta 1 dot here and del 2 dot. So, this is what is meaning of this one. Okay. So, when I do del k by del theta 1, so basically what I am going to have this constant term into theta 1 dot. So, this is what I have, and when I am doing del k by del d2 dot, then I am going to take the derivative of this one. So, it is going to be m2 d2 dot. So, this is actually m2 d2 dot. Okay. So, this way we can get it. Then I can evaluate del k by del theta. So, here I do not have any term in the theta in this expression, in this expression. So, this is going to be 0, and when I am doing it by del k by del d2 here. So, I have a term in the d2 here. Okay. So, this is what I am going to get, m2 d2 and theta 1 square. This is how I get this term. Then I have the potential energy term already. So, this I can differentiate with respect to say the two generalized coordinate. Okay. So, the first one will be basically here, it means that del u upon del theta 1, and then it is del u upon del d2 basically. Okay. So, when I do it by del theta 1, so here you can see that we have g m1 L1 plus m2 d2, and derivative of sin theta 1 will be cos theta 1. Okay. And in the second one here I have to take the derivative with respect to d2. So, what I am going to have basically, I am going to have this g, this term is going to be 0, and m2 sin theta 1. So, g m2 sin theta 1 here. We can see that this constant term does not contribute anything to any of the term associated in the evaluating the Lagrangian equation. Okay. So, when I can substitute these values now here. So, I have this d by dt, and this is this term basically, right, which we have evaluated. This is the derivative here. Okay. And the second term is this one, and my third term is this one. Okay. And so, this is equal to tau 1 tau 2, and now I take the derivative of this one. So, my this whole term is here, I have theta 1 double dot over here, and this one, this derivative, this was derivative already. So, now when I take one derivative. So, I am going to get the d2 double derivative. Okay. So, this is what it is going to be, and my second term is as it is, and similarly my third term is as it is. So, this is my tau 1 tau 2. Okay. So, the final value of the torque force I can write these values. Okay. So, whatever I got from this equation, okay, the first term and second term, now I am writing separately. So, here I am putting up the coefficients of theta 1 double dot. Then we have the two velocities, okay, the two generalized velocities here product, and we have a term which is associated with g. So, this is for the first joint and this is for the second joint similarly. So, we have d2 double dot and we have theta 1 dot square, and there is a term with g. Okay. So, now if I write this in the matrix form, so this way, okay, tau 1 tau 2 and these two terms written here, and here I am writing the double derivative of the my two generalized coordinates. Okay. So, I get this term from here because here I have got theta 1 double dot and there is no d2 double dot term associated in the first expression. So, this is 0 here. Similarly, there is in this one there is no theta 1 double dot term. So, 0 here and here m2 is there. Okay. And then I am putting up this term where I have the two generalized velocities, okay, here, and the g terms are here. Okay. Similarly, for the second equation I have the velocity square, okay, and the g term is here. Okay. So, I can write this in a matrix form or as a shorter notation. So, this is tau, okay, tau vector. This I call as a matrix which is going to be function of theta, and we have this theta double dot vector, and this hold all these terms I am writing this with theta theta dot, and these terms I am writing as g theta. Okay. So, this matrix which is coming over here, this is what we call as the mass matrix of the manipulator. I am going to again talk much more details about all these in my next lecture, where I am going to discuss a lot about the state space form of the manipulator dynamic equation. In fact, this is the state space form of the manipulator dynamic equation, because this representation involves both the theta and theta dot terms. Okay. So, that is there. So, this term is the mass matrix and this term is a vector of centrifugal and the Coriolis term over here, and the last term, this term is vector of the gravity terms over here. So, to summarize, we define Lagrangian as the difference between the kinetic and potential energy, and this Lagrangian encodes all dynamics in two scalar energy functions. Okay. And this is how we finally express the manipulator dynamic equation. Okay. So, next class I am going to discuss a lot about this form of the dynamic equation and how we can further exploit these equation for the manipulator dynamics, manipulator control and all. Okay. So, with this, these are the references for your further studies, and thank you.